Okay, guys, I promised that I would follow up with another discussion of Project 4, beginning with the detailed block diagram, just to talk about the different uh, parts of the design that you'll see when I go through. What you can see behind is the Verilog. So this design, we have the buttons, three of the buttons to control our logic. We have switches that we use to configure, and we then have our three debounce circuits. That's why in the previous lecture I presented them as its own separate module. It makes it easy to instantiate in our design. Then we need a loadable register. Then we need our register file, and we need our ALU. So tonight I want to walk through the architecture, more so from the implementation than from the overview. So let's just jump in. So we're going to start off. We're bringing in our switches. We also, in this case, our buttons. We're also bringing in our reset on button 0. So what you need to do is no longer have a reset in your port list, but you then need to be able to take the input buttons, which is 4 bits wide, 3 to 0. Button sub 0 drives reset. Then we have the different definitions that we're going to need in order to implement our design. So included in here is the 7-segment display, the debounce, the loadable register, the ALU, the register file. Everything is going to be in this design. So as we scroll down, the next thing we can see is where I instantiated the debounce. Having a separate module makes it very easy to then just give yourself 3 instantiations of our debounce PED, which is basically going to take buttons 1 through 3 and allow them to be debounced and then to generate the one clock wide output when we so desire. So we instantiate it. Our input changes 1, 2, 3, and our outputs are unique. So button 1 is the load switches, button 2 is the write reg, button 3 is the do op. And just to refresh ourselves, if we come back and look here, the write reg is meant, let's start off with the load switch. The load switches is meant to take the information on our 16 switches and copy them into a register that we could then use in our design. So no matter what, we always start off with a load switch where we put a certain pattern on the switches and we press the button 1, which will copy it into the loadable register. Now notice we take the 7 or the 8 LSBs out of that and we run it out the 7-segment display 31 to 24. So you should get an immediate feedback whenever you load the switches. Whatever pattern is on the 8 LSBs, you should immediately see on the upper 2 digits. Then once we have our switches loaded, then if we're filling the register file with our data, we press button 2, which gives us a write reg, which will select the data that we've loaded to be put into the register file, and will also then tell the register file to capture the data. Finally, the third button is when we want to do an operation. So we would have loaded our switches with a pattern that would have filled in the addresses for our 2 operands, what the opcode is, and we would then be able to then perform an operation that would pass the data through the ALU, and we would be able to bring it back and write it into a register. So that's the architecture that we're looking at right now. So starting off, we have our 3 debounce implementations. Now the way I've designed this is I put all of the combinational logic into one always block, all the sequential logic into a second always block. So as we walk down, we're going to be looking at it functionality by functionality. So the first thing I'm doing here is I call the output of my loadable register with the switches switch Q. And now I've generated the different fields that I want to use inside of my design. So data represents the 8 LSBs. That's the data I want to write directly in. Opcode represents the 3 LSBs. Even though they're the same, the use is different. We use them at different times. So sometimes those LSBs are used for the data. Sometimes they're used for our opcode. Then we have our fields for the write address and the 2 operands. So all I'm doing here is taking the switch register and partitioning it into fields that I could then use and know exactly what I'm looking at. When I want to load my switches, I have the load switch, which takes the switches and puts it into the next switches. Else, I take the switches and give it back. So this is the combo logic in front of the switches. Then this is a repeat. This is our 7-segment display where I'm taking the information to give it to my 7-segment display. So I have 8 different portions that I'm able to select from. And you can see I'm looking at the output of the ALU, register B, read data B, read data A, and the switch Q. So let's just go back to our top level module again real quick, and we can see what I'm doing. For the switches, the data, I take those through the 7 segments 31 to 24. That, of course, is 8 bits, but I'm outputting 4 bits at a time. That's why it shows up twice, and we'll look at it again in a moment. Then we want to see what's on our read data A. We'll see on those bits. We will be able to see what's on our read data B on these bits. And finally, we'll be able to see what's on the ALU output on those bits. So that allows us, as we're going through the implementation of the design on the board, and we are loading information, that we will be able to observe the results. And that's the purpose of the spreadsheet I gave you in the project for helps, that it shows you exactly how to provide the stimulus to the design. Then you could record what should be happening as the data is moving through. So there's our 7-segment display inputs, the nibbles. The cathode is the same as it always is. Those are our 0 through F. There's my tick, giving me my 1 millisecond pulse, just like in the previous. There's my counter for updating the display. There's my anode rotate, along with the counter for switching the cathode selects. Now we get to the new stuff. Now we get to our ALU. And as I've tried to say, the implementation of the ALU is really fairly straightforward for us. If we were designing a real processor, the ALU would be an intricate design, because how the processor is able to perform the arithmetic and logical operations is particularly time critical. But for us, in our simple little world, we're able to implement our ALU as a case statement where we're making the decision based on which opcode is being presented to the design. And depending on the opcode, we perform different operations, be it addition, subtraction, logical left shift, the rotate, an and, an or, an exclusive or we just complement the whatever's in read data A. Up here, we have the ability to keep track and generate our flags. So the carry is just represented by ALU out bit 8. So you can see when I defined ALU out, I didn't define it only as an 8-bit register, I defined it as a 9-bit register. So that when I do the addition, if that carry bit gets generated, I'll be able to see it. And my 0 flag says when I OR all of the bits of ALU out, the OR reduction OR says OR all of the bits. And what it's checking for is any bit of 1. If there is no 1 in this register, then what happens is the output will be a 0. And then what I do, I complement it to show that when every bit in ALU out is a 0, I set the flag 0. Now, we've mentioned that the ALU, or the register file, has 2 read paths to produce the 2 operands. Since they're just combinational paths, we can just set it up where we have a pointer to our register file, and the output of that pointer provides the operand. So register address A gives us register data A. Read address B gives us read data B. And then we needed a control signal for our loading of the register. So we ORed together do-op and write reg to get the actual load reg signal. So that's what we're looking at here. So that is all the combinational logic I needed for our register file and design. Now, here what I have are the sequential elements. These are the flops. So there's my switches that I'm just assigning the next to, my counter, and the anode. Now, the most interesting here might be the register file, in that I'm concerned about when we're writing the data. So let's start here. So if load reg is active, then I will write either the data from my switches or the result of my ALU operation into my register file. And so I use the write reg signal as a select. So if I'm loading and it's a write reg, I'm going to put the data in. If I'm loading and it's not a write reg, that means I'm performing an ALU operation. I will then copy the contents of my ALU out back into my register file at the address I was pointing to. Verilog also allows me to have a reset of a 2-dimensional structure. So in this case, at reset, it allows me to say fill all 8 of my locations of my register file with 0. So that is the content of the design. And let me come back up to peek again at the definition of our memory and see if I can find it here. So there's our register file. We've defined every location as 8 bits wide, and then we have the addresses. The LS address is 0, the MS address is 1. So that was the design. So let's take a little peek at a couple other blocks I gave. I gave you an ALU test bench. Now to use this, you would have had to implement your ALU as a standalone module that you could have then instantiated. Then this guy walked through and performed all the different operations and checked the outputs. I got a little help that I might have had a bug in it, but for the most part, I think it runs pretty clean. So you have that on Beachboard for you to be able to download. Sorry, it's wigging out here. Let me just close these guys. Now, what I wanted to get to, what I'm fishing for now, is just a simple test fixture for our design as it is. So here, I've defined the ports. I have then instantiated my top level design. Because in my design I wanted to use the terminology that I understood, I then concatenated them together to generate the button input to my design. There is the generation of the system clock. Here's my initialization of all my variables. I wait 100, turn reset off, then I wait 100. Now what I've done is I wrote system tasks, and we'll take a peek at them because this makes it easy. It makes it easy for me to load a register with a particular value, and I don't have to write that code over and over again. So what I'm doing here, this is exactly follows the sequence that's on the grid that I gave you guys. I'm loading 1s into address 0, 2s into address 1, 3s into address 3, 4, and so on. I got goofed up. To 0, to 1, to 2, to 3, to 4, to 5, to 6, to 7. Then what I wanted to do, I wanted to come in and do the 8 operations. So this corresponds to exactly what I'm asking you guys to do with the spreadsheet. Now let's take a peek at a task in Verilog. So the task is outside of it's outside of your code. It's inside of the module. You have the keywords task and in task. You can have input operands. So each of these represents an operand that I'm supplying to the task. In this case, for the load reg, it's 16 bits wide. Then I come in, I take that input, I assign it to the switches. I then give some feedback of what's going on. I set the load switch. I wait long enough to get through the debounce. I then wait long enough to get through the debounce when I'm leaving. And then I'm done. So I'm doing my load switches, then my load reg. So that should get through my debounce circuitry. So what I'm doing here in the load reg, like I mentioned, I'm just filling up the 8 registers with a known pattern. That allows us then to do the operations using the ALU. This time I want to be able to anticipate what's happening. So here what I'm doing is the same. I'm doing the load switch, but this time the second step, instead of the write reg, what I'm doing is the operation itself. So I load this data into the switches, then I tell it to do the operation. This would then go through all 8 different combinations and perform all 8 ALU operations. Then finally in my display, let me come down here. And what I'm doing is I'm displaying the contents of all of my design. And what I did, I cheated a little bit here because I wanted to see what was happening inside of the design. So Verilog allows you, so let's just look at this. I want everything in pink, I want to be the text when I run the simulation. So it says 31 to 24. Then it says I'm going to give it an argument and I want it to be displayed in hexadecimal. Then this is more text followed by an argument in hex, more text, an argument in hex, more text, and so on. Then what I do, I peek into my design. Since this is a simulation, there's no problem here. And I say, okay, I want to see in my instance P4. So let's just go up here and look here real quick again. Notice when I instantiated my design, I gave it an instance name of P4. That allows me then in Verilog Ease to be able to reference data inside of that module. So I want to see the switches. I want to see what's on read data A, what's on read data B. I want to see what's on ALU out. Then I want to see what's on the carry and the zero. So really what I was doing, I said, okay, show me what I'm going to see when I run my design. So that is an overview of Project 4. It's more complicated, but I think it's absolutely within our grasp. I hope that everybody's putting in the time to be able to get it done. This week I will introduce state machines, and then we will have a discussion about the next project. Okay, study hard, you guys.